Hi folks, we're going to take a look at number 11 on page 419. So here they tell us that there's a 10 kilogram mass that's suspended by two pieces of string. They give us the length of those strings, and they tell us that it's suspended from 2 points that are 50 centimeters apart at the same level. All right, so they want us to then find the tension in each piece of string. So what I always suggest in these types of questions is to first draw a situational diagram. So draw what the situation is representing, and then separately draw a force diagram that you're going to use to solve the problem. All right, so let's say I've got my mass that's suspended from these 2 points 50 centimeters apart. Okay, and they're suspended by two strings, so one is going to be 40 centimeters long and the other one's going to be 30 centimeters long. It'll be smaller, so I'll try to draw a little smaller. So what I'm given are the lengths of these strings and the distance between where they're attached, and then I've got my 10 kilogram mass. All right, so let's figure out all the forces that are acting on this object. And before I do that, let's keep in mind that this mass is suspended, meaning it's not moving. So that means that the net force, meaning when I add up all the forces acting on it, should add up to 0. Okay, so I've got the tensions in the two strings. So going in that direction of the first string, that direction of the second string. All right, and then of course we've got the force due to gravity going downwards. All right, so what I want to do now is I want to take these three forces and I want to draw a force diagram. Okay, and the important thing, as we just talked about, is that I know that these three forces have to add up to 0. So when I draw this force diagram, I know it's going to have to form a closed shape. In this case here, it's going to form a triangle because I'm only dealing with three forces. All right, so let's try to draw this. I would say start with the easiest force, which is the force due to gravity, so going downwards. And this is where I already run into a bit of trouble, because I'm not sure how I'm going to draw these other two forces. Okay, I don't know their magnitudes yet, but I don't even know their directions. So even if I wanted to draw, one force going there, and then I know it's going to have to form that closed triangle so that the sum just gives me 0. I'm going to need those angles. So this is what makes it different from the one that would have been solved in the lesson. So step number 1 is to determine these angles. So I'll call this angle theta. This is the one I'm going to look for because it's inside the triangle. Why is that useful? Because that's going to be the same as this angle here, because that's also theta. This angle here, say I call it phi, which represents the angle with respect to the horizontal of the second tension, is going to be the same as this other angle in the triangle. So that's why it was important for them to tell us that it was at the same level. So I knew that I was dealing with something that was horizontal. All right. Now, by the way, I am noticing that these numbers 30, 40, 50 form a very special triangle, but I'm going to pretend I didn't see that because I just want to show you what the scenario would be, how you'd go about doing it if you didn't recognize this as being a particularly special triangle. Okay, so I'm just going to go ahead and solve for these. So I know the three sides of this triangle. So if I start with theta here, I'm just going to use the cosine law. So it's going to be cos inverse. All right, and then here I'm going to start with the opposite side, 30. So it's going to be 30 squared. And then I'm going to subtract the square of the other two sides. So minus 40 squared, minus 50 squared. All right, and then divide by -2 times these two lengths, 40 times 50. Okay, now if you feel more comfortable starting with the traditional cosine law and then solving for your angle, you can do that too. But hopefully you're comfortable just remembering how to find the angle directly. All right, so let me take the calculator and let's calculate this here. And again, the trick is to make sure you're careful with those brackets and turning the calculator on. That helps. So cos inverse, open up a bracket for the numerator, 30 squared minus 40 squared minus 50 squared. Close the bracket, divided by, open up another bracket for the denominator, -2 times 40 times 50. All right, and here we get, looks like 36.9 degrees. All right, so let's do the same thing to find the other angle. Now, again, I always try to avoid anytime I'm working with one angle and two side lengths, even though I can figure out whether, I don't want to have to think about whether the ambiguous case of the sine law even applies. So since I know the cosine law so well, I just go ahead and use the cosine law. Now, if you know two of the angles already in the triangle, then there's no issue with using the sine law. All right, so here now I'm looking for phi. So its opposite side is 40, so it's going to be 40 squared minus 30 squared minus 50 squared all over negative 2 times 30 times 50. All right, so let's calculate this angle here. Okay, so cos inverse, open the bracket, 40 squared minus 30 squared minus 50 squared, close bracket, divided by, open up another bracket, negative 2 times 30 times 50. And here we get 53.1 degrees. Okay. Now again, you might be seeing, yes, something very nice about these two angles, but I'm not going to, like I said, I'm going to pretend I'm not seeing it, because in most scenarios, this won't be such a special triangle. Okay, but now I can start drawing these angles. So let me call this one here string 1, and let's call this string 2. Okay, so I know the force due to gravity. Okay, I know its magnitude because once they give me the mass, I know that the force due to gravity is just 9.8 times the mass. Force equals mass times acceleration. All right, so 9.8, the acceleration due to gravity. So this is going to be 98 newtons. Okay, and what I can draw now is, let's draw this force 2 first. Just easier, I've got more room on the right. So here, when I draw this vector, well, remember, phi is equal to 53.1. All right, so if this is equal to 53.1, I'll be able to calculate that angle inside the triangle. So that's going to be useful. All right, now, notice I don't know its magnitude. Remember that 30, 40, 50, these were just side lengths. Okay, now what I do know is that this angle, this force going in the direction of the first string is going to have to close off the triangle. Why? Because this mass is in equilibrium, so it means that when I add the three forces together, they have to form a closed shape, so the sum is equal to 0. I end up back where I started. Okay, but here this angle theta is just 36.9. Okay, 36.9, and then if I want to calculate this angle here, well, these two angles are going to be the same because of the parallel line principle, 53.1, and then lo and behold, when I add these two things together, I get exactly 90 degrees. Now, of course, we had seen that earlier, the 3, 4, 5 triangle, but again, you can't assume that it's always going to be a right angle triangle. Okay, now this angle here, if this is 53.1, this is a 90 degree angle, so that's complementary, so that's just going to be 36.9. I don't even need to calculate this angle here because I'm working with a right angle triangle. Now, if I wasn't, I just want to say something about what I would use to solve this problem. If it wasn't a 90 degree angle, I would use the sine law. And I would be perfectly fine using the sine law because I know two of the angles. Once you know two of the angles in a triangle, the third one is automatically known. So you don't have that issue with the ambiguous case of the sine law. That's only an issue when you're working with one angle and two side lengths. Okay, but since this is a right angle triangle, I'm going to use the simpler trigonometry. Okay, so let's call this was the second string, so we'll call this the magnitude of T2, and this length here will be the magnitude of T1. All right, so if I want to find T1, here's my 90 degree angle, there's my hypotenuse, so I'm going to use sine, so I have sine of 36.9 degrees is equal to the opposite, magnitude of T1 over hypotenuse, 98. Okay, so magnitude of T1, which is one of the things I'm looking for, the tension in the string. Okay, so let's calculate that. So it's sine of 36.9 times 98. Okay, and that's 58.8. And since it's the magnitude of force, it's going to be in newtons. All right, now let's calculate the magnitude of T2. So here I'm just going to use cosine. So cosine of 36.9 degrees. Okay, notice I'm not going to use tangent because remember the magnitude of T1 is an approximation. As much as possible, you want to try to use the exact values. So this is going to be the adjacent side, magnitude of T2 over 98, the hypotenuse. So magnitude of T2, which is the other thing I'm looking for, the other tension, is just going to be cosine of 36.9 times 98. And that gives me, I feel like that's, let me check that again, cos of 36.9, okay, times 98, yeah, 78.4, I had done it right. Okay, 78.4 newtons. All right, and there we have it. So here, when they're just asking for the tension in the string, you just have to give the magnitude because obviously the direction is the direction that the string is going to. All right, so let's just recap here. Step number 1, draw your situational diagram. Step number 2 was to realize that you couldn't quite draw your force diagram yet because you needed the angles in order to do that. So you used cosine law to help you find the angles because you knew all 3 sides of this triangle. From there, you could then draw your force diagram, which needed to be a triangle, a closed shape, because this mass is in equilibrium. So the sum of all 3 vectors has to be 0. And then it happened to turn out that this was a 90-degree triangle. Of course, if it wasn't, I'd likely be using sine and cosine law in that case there. Okay, that's it for this one.